Good day. This is the fifth in a series of videos designed to explain how to create predictive models which are simultaneously explicable and precise. As we promised in the last video, in this video we will be discussing how to create groups of an increasing target variable. And we'll explain what that means along the way and how to do it. We will also take into account various numerical considerations as we go. So without further ado, here we go. So, simply put, there are times when you're doing predictive modeling when values of a variable need to be grouped together. And so here are some examples. So if you're doing auto insurance, one of the things that's true is that rates need to go up with DUIs. If you're doing commercial liability, they need to go up with square footage. If you're doing workman's comp, they need to go up with patient or with payroll. If you're doing medical malpractice, it needs to go up with patient volume. And just generally, if you have some sort of predictive model already built on your data, like we are doing in this particular example with respect to housing prices that we started in the last video, we've already at this point created some models using both XGBoost and Random Forest. And so now the question is, okay, we have these models, what do we do with them? Well, we have this model output. Among other things, what that allows us to do is to order the values of our various categorical variables. And similarly, rates need to go down if you're talking, again, insurance, if you're talking about years claims free, right? Like that's got to count for something. I haven't had a claim in 5 years. Hey, can you give me a break on the price? The age of a moving violation, you would say, oh, that speeding ticket was 4 years ago. Who cares? Come on, give me a break. Maybe the age of the newest account. If you're taking a look at someone's financial history and all of their accounts are way old, it's like, okay, this guy's got a pretty stable financial history here. Things are okay. And again, the last thing you want to do with any of these things is violate them because that creates what we typically refer to as moral hazard. So if you're an auto insurer and you can't say to a fellow, hey, if you could just get one more DUI, I can give you a break on the price. The rates need to go down with DUIs. All right, all well and good, but how do you go about enacting this? Well, let's take a very simple example here with very easy numbers with which to work. So this is an example involving speeding tickets, and so we look at the people with speeding tickets, and what do we see? We say, okay, well, look, we've already got some groups here, right? Because we just put 5+ in there, and there's the same amount of weight in each category here, and here's the associated average loss per category. And so what do we see is that the average loss per number of speeding tickets mostly goes up, right? It mostly goes up. But in the case of, moving from 2 to 3 here, it kind of goes up, goes down, and goes back up, right? So what do we do about it? How do we group these things together in some reasonable fashion? Well, one thing you might do is you might say, okay, well, what if we just took the first two groups, people with 1 and 2 tickets, and grouped them together? So, there's an even amount of weight in both groups here. And so therefore, the average loss for them is just going to be the average of these two numbers here, which is 175. And when you do that, and then you compare the grouped value with the individual values, what that does is that creates a squared error of 562,500. And go, okay, well, that's what would happen if we grouped together people with 1 and 2 speeding tickets. Well, what if we group 2 and 3 together? And so what happened there? Well, when you do that again, the average loss for each person in this group is going to be $237.50. You get a smaller attendance squared error when you use these values and compare them to these values. And just for the fun of it, right, we might go, well, what happens if we group 3 and 4 together? Well, again, you get stuff that's increasing, like we did in the first two examples here of grouping. But the error associated to this, when you use these values here and compare them to the individual values, the error gets much larger, right? So of those 3 scenarios, you go, I'll probably go with grouping 2 and 3 together. But the fact of the matter is that, we could have even taken things, say, 3 at a time, right? We could have looked at grouping 1, 2, and 3, or 2, 3, 4, or 3, 4, 5 together. We could have done things 4 at a time, and so on. And so even in this small example, things get to be somewhat complicated if you really start thinking through all of the different possibilities and all the ways you can group these things together so that you get an increasing average output. And that's just with 5 records. So how do you solve the problem systematically in any reasonable way? And so this comes from a data set that I simply fabricated, and you'll see that in the code, which is publicly available on GitHub. Uh, how do you do this systematically? So here's an example of 101 different groups, or you can think of it as 101 different records in your data, and you have to group them such that you go from something that looks like this, which is mostly increasing, although there's some noise down here, a little bit up here, to something that looks like this, where it's like, boom, everything's just increasing all along the way because we group things appropriately. How do you move from one to the other in some systematic fashion? Okay, now you might be asking yourself, 101? That's kind of weird. Why did you choose that instead of 100? You'll see momentarily. So to answer this question, we have to formulate this problem mathematically so that we can solve it generally, right? And so here's the first thing. So let's return to the original example of speeding tickets and say, yeah, this is how we saw it originally, which was speeding tickets, some sense of weight, and some sense of average loss. But the real general formulation of this problem is as follows. It's ordering variable, weight variable, and target variable. And that is the general setup for this kind of problem. Is you have 3 variables. You have some way that you are ordering your data, because you need to talk about increase and decrease, which means there's a sense of order. There's sometimes a weight. If there is no obvious weight, then the weight is just all ones or equal. And then there is a target variable. There's something that you was seen empirically and that you are trying to group together according to the ordering variable so that things go up. And so this is what we decided upon in the previous slide. We said, okay, we're going to group these 2 guys together. And why do we do that? Well, it's because, when you have this mean that comes out of it, you get a small sum of squared errors. And so what do we learn from this small example? Well, we say, well, look, if there was a grouping, each element would be represented by the mean of the group. And so that's what we're doing here, right? Is that when we group together 2 and 3, we think of these things as being the same in the grouping. That's the whole point of being a group, right? Is that everything in there is interchangeable. And then we would basically assign the same risk to both of these guys. If you're a 2, you have a risk of 237.50. If you're a 3, you have a risk of 237.50, and everyone else simply gets the risk associated to them. And again, we selected that because there seemed to be some sort of minimization of squared errors that went along with it. And so what is a grouping then? Well, a grouping it's a vector of increasing components. And what we would think of is that each equal values of the vector of increasing components correspond to the mean of the target variables for those records. And so that's what we're doing here. Now, how do you find such a vector? Well, the answer is, well, you go, we recall that when you're looking at a weighted average, so this is your standard weighted average here, it's your weight times the target divided by the sum of the weights. Recall that the weighted average is actually the solution to a minimization problem. In particular, the weighted average minimizes the weighted sum of squared errors. And so therefore, when we're thinking about guys that are in a group together, whatever number in the previous slide being 237.50, whatever number we use to represent those values there, we would expect that number to be the weighted average of the target values of the variable in there. So what are we going to do? Well, we're going to solve a constrained optimization problem. We're going to say, hey, I would really, really like to get a vector of increasing components. And then we're going, which minimizes the sum of squared errors. And then we're just going to look and see when we do that, which of the components of the solution vector are the same. And those are going to be the ones that give us a clue about which elements we should group together. Okay. And so now this is going to be yet another video where we go back and forth between a few different applications here. So here we go. Let's go and talk to our good friend Excel. Okay, so what are we doing here in Excel? Well, look, here's the deal: is that this is obviously from the previous slide here. This is an example of how we go about doing this. We say to ourselves, well, look, you've got this phenomenon here. That's the target variable. You have this phenomenon of interest. It's going up, it's going down. It's clearly mostly going up, right? But it's kind of bumpy. There's some noise. We need to group these things together. And we say, okay, well, we remember the strategy. What we would like to do is we would like to solve a constrained optimization problem. We want to solve for the following. We want a vector here where all of these things are increasing and it minimizes the sum of squared errors. So if you look at the formula here, and always remember, if you can't do something in Excel, you don't understand it. You should always first try all of your ideas in Excel because you can play at the cell level. It's great for small problems. So if you look here at the formula for the error, it's the weight multiplied by what you actually observe in the data. That's your target variable. And then you're comparing that with what we refer to as the group target. So column F here is what's going to change here. So what we want to do is we want to make column F such that it's increasing. But of course, when we change values in column F away from values in column E, then the error here is going to be non-zero, right? But we want to keep that error as small as possible. So how do we do that? Well, we have our good friend, Mr. Solver, here in Excel. And so we say, okay, the total error, so just real briefly here, the total error here is the sum of the individual errors. Each of these individual errors is weighted by the weight for that record. So that's the sum of them. And so we are going to minimize the total error. We're going to do that by changing the values here in column F. And then we are going to consider this constraint here. And so the constraint is saying, look, I want all of these guys here to be less than or equal to these guys here. Now, in Excel, you have a few limitations on what Solver can do. So, one, it can only handle up to 200 variables, and two, it can only handle up to 100 constraints. And so if you have only 100 constraints, that means that you can perform this analysis only on 101 records, which is why it shows that number. So that's the general setup here in Excel. However, if you want to do this, say, in something like R or something like Python or something like SAS or something like that, you need to figure out how to set things up in that environment so that you can perform a constrained optimization problem. And so now let's go to our good friend R and talk about how we do that there. So here we go. So now we're in our good friend R. So first thing that we do is we create the sample data set. We check the creation. Yep. The ordering variable is going up the way it should be. So that's good. That makes us feel good that we created that correctly. Next, if you write it to the disk, you can see here in the code that I don't really have a file path there, but you can write it to the disk on your computer, and that will give you precisely the Excel file that you saw previously, or it gives you the input to the Excel file that you saw previously. So here in R, we have to, it's a little bit more technical than Excel, right? But it's more powerful. So, hey, life is full of trade-offs. But we simply create our objective function here. So in Excel, we had that one cell, which was the sum of all those other cells in the column, each one of those cells in the column was itself a squared error that was weighted, and then you add it up. And here in R, we are doing exactly the same thing, which is that we have our target variable, the value to which we're comparing it. This is the squared error here. And then it's weighted, and then we're adding all that up. So that is the sum of squared errors represented here in R with the function notation. But now, how are we going to implement constraints in R? And the answer is there is a package called the Alabama package. And in particular, it contains a function called the auglag function, which solves constrained optimization problems, and whose author is a very nice person. I've corresponded with him a few times, asking him questions about this and that. And he was very communicative, and it's a very fast and well-written package. And so, great experience thus far. But here's the thing, is that the way R thinks about, or rather the auglag function thinks about inequalities, is it says, look, whatever conditions you want to have hold this thing less or equal to that thing, what I want you to do is I want you to take your condition, I want you to move everything to the right-hand side of it so that all of your inequality conditions are of the following form. 0 is less than or equal to some function. 0 is less than or equal to some function. That's how inequalities are supposed to be written if you want to make use of the auglag package. And so then we say to ourselves, okay, well, gee whiz, how on earth do you do something like that? Okay, well, for one thing, we know that we want x2, the second component of our vector, bigger than x1, the first component of our vector. So if we want x2 bigger than x1, that's equivalent to x2 minus x1 being greater than or equal to 0. Similarly, if we want x3 bigger than x2, well, what that means is that we want x3 minus x2 to be greater than or equal to 0. And same thing with x4 being bigger than x3. x4 minus x3 has to be greater than or equal to 0. So how does this look in practice? Well, again, before doing it in R, you should always do it in Excel. So we're going to go back to that now. So you go flip back to Excel, and that's the whole purpose of this tab here, increasing groups O2. Is now our constraints. What is going on here with the constraints? We have a constraint column. We didn't have that over here. So we got a constraint column. And what's it doing? Well, apparently, you can tell by the braces here that this is an array command in Excel. And so if you look at the formula here, it's clearly making use of column F. What's it doing? Well, it's doing matrix multiplication of column F on something else. What's that something else? Well, that's the inequality Jacobian matrix here. And so the way to think about this then, this formula here, is that what you are doing is you are taking this vector here and you are multiplying it on the right-hand side of some matrix. What is that matrix? This matrix here. So what's going on? Well, when you, and this matrix contains mostly zeros, I've color-coded it so that the negative ones are red and the ones are green, and then everything else is just 0. So this is a matrix here, and it's got 101 columns. It's got 101 columns because you have 101 components in your vector that you're going to be multiplying this by. So those have to be equal. And it's got 100 rows. Why does it have 100 rows? It's got 100 rows because what it's doing is you have one row for each inequality. So x2's got to be, x2 minus x1 has got to be greater than 0. x3 minus x2 has to be greater than 0, greater than or equal to 0. x4 minus x3 has to be greater than or equal to 0. And that's precisely what you get when you take a vector of 101 components and multiply it by this matrix. The first row here, because there's a -1 in column 1 and a 1 in column 2, gives you precisely negative x1 plus x2, which is equivalent to x2 minus x1. row 2 here, there's a -1 in the second column and a 1 in the third column. When you multiply that by your vector, you get x3 minus x2, and so on. Okay, so what we've done here is instead of incorporating the constraints directly into solver as we did in the previous tab, if you look here, what have we done? We have the same objective function, the sum of squared errors. But now what are we doing? Well, we're changing our grouping targets as we did previously, but now our constraints are, hey, look, just make all these guys greater than or equal to 0. That's what we want to have happen here. And so now we have mimicked in Excel what we are doing formally in R. Is we've got just a bunch of functions and we're saying make them all bigger than, greater than or equal to 0, move everything to one side of the equality. Okay, and so now what I want to do is I want to run this here in Excel. So we're going to let that guy go about his business. And now while that guy's running, we're going to flip back to our studio. So flipping back to our studio. Boom. Okay. So that matrix that you just saw in Excel there is precisely what we're creating here when we create the inequality function Jacobian matrix. Now, the Jacobian should be distinguished from the Jacobin, which is political, and the Jacobian, which is aesthetic. The Jacobian is the matrix of gradients. So for every inequality function, so you've got 101 input variables, right? And you've got 100 different inequalities. Each one of those inequalities is a single function. So it's got a gradient of length 101 because you have 101 input variables. And so you've got a gradient then for each one of those inequalities that you want satisfied. All well and good. And so that's what the Jacobian is generally. In this particular case, the Jacobian is simply because all of our inequalities are linear, it's just a constant matrix. And so when you look at that matrix then inside of R, it looks exactly like it does inside of Excel. First row, -1, 1. Second row, -1, 1. Third row, -1, 1, and so on. So that's what's going on there. So now that we've got that guy, and we already made the argument that we can express the inequalities as simply multiplying x by that matrix, now we're in good shape. So now we just want this inequality function, which is vector valued. We want each of the components in the vector to be greater than or equal to 0. We load the Alabama library. And now I want to start making points about numerical considerations when you're doing that. So I'm actually going to run this constrained optimization in auglag 10 times, and I'm going to be doing this all throughout the presentation here because I want to make a point about speed. So here we go. So we're running it 10 times, auglag. If you don't turn it off, it's a very verbose subroutine. It prints all of these steps so you can see things changing along the way. You can see what it's grouping together and all that good stuff. So yeah, it's going about its business. Okay, so there we go. So we just ran this thing 10 times. And I am going to be keeping track of this throughout the presentation in the summary data table. So we just used the constrained optimization, and we just said, hey, minimize this subject to that. Here's your initial value. Have a nice day. That's what we said to the auglag function here. It said, okay. And so it goes about its business. It computes a bunch of values. It comes back with an answer. It says, here you go. So thank you very much. How long did that take, Mr. Auglag? And it's like, well, we did it 10 times because, we want to get some sort of stable sense of how long it takes. On average, it took about 1.8 seconds to run that constrained optimization problem. 101 input variables, 100 constraints. Meanwhile, we check back to Excel. Excel Solver is still running. So already we're seeing the advantage of doing things somewhat more procedurally, somewhat more abstractly, somewhat more mathematically in R and presumably Python, though I haven't implemented it there, because the speed greatly outstrips Excel. We've already put it in the dust. Okay, so that leads us nicely into talking about some numerical considerations. Okay, so there are some numerical considerations when you're doing this work here. And the first one is that formulaic differentiation materially speeds up computations. So we'll talk about that formally in a moment. But the idea is basically this, is that we all know from Calc 1 that the derivative of x squared is 2x. But the computer doesn't know that. The computer doesn't know what you're up to. All it knows is you handed it a function, and you said, hey, please optimize this, Mr. Computer. And it says, okay, I'll do my best. And so what the computer is presumably doing is it's implementing some sort of what's known as gradient descent algorithm. Gradient descent algorithms, as the name suggests, imply that some sort of computation of a gradient is involved there. And if the computation of a gradient is involved, well, then what that means is that if you don't tell the optimization routine, oh, by the way, this is the gradient of this objective function, it's just going to numerically estimate it at each step of the algorithm, at each step of the iteration. And so presumably then if you just handed it a formula and said, just use this instead of having it estimated numerically, that's going to speed up computation. We'll see that momentarily. The other thing is we sloughed over this detail previously, but we should talk about it now, is, and we'll see this momentarily in Excel, is that the components of the solution vector, we said, which are the same, indicate the elements of the group. And so this is going to be the outcome of some of the Excel work that we're doing. So these are records 3 through 6. And what you see is, okay, well, when we solve the constrained optimization problem there, records 3 and 4, they get the same value, and records 5 and 6 get the same value, and go, okay, cool. Well, let's just group those guys together, and everything should be fine, right? Well, the question is, what is meant by the same? And so the point here is that, yeah, they're the same at 1, 2, 3, 4. 1, 2, 3, 4. They're the same at 7 decimal places, but they're not the same at 8 decimal places. So what's the correct answer? Is it 3, 3, 4, 4, or is it 3, 3, 4, 5? And we'll see how to answer that momentarily. Okay, so we now return to our good friend, Mr. Excel, and we see what he's been up to. And so finally, he comes back with his solution. It took you long enough, pal. And so we say, thanks for doing that. So you can see that in the constraint column, all of our values here are 0 or greater, so good for us. And now we've got a vector of increasing components here that supposedly minimizes the sum of squared error. Now, one of the things about Excel that you should always keep in mind is it doesn't always give you the right answer, like right off the bat. Sometimes it needs a little encouragement. So we are going to provide it some by running it again. So keep in mind the total error right now is 196239. We should see that go down over time, but it's still going to grind around, and you can see it. Whoops. You can see it grinding around right there. Yeah, it's at the, 4th decimal point or something like that. But hey, you want to try to get as much power out of these things as you can. All right. So going back then to R, let's talk about provision of formulaic derivatives. All right. So going back to our good friend RStudio. Fortunately for us, we say to ourselves, hey, wait a minute. We took Calc 3. We feel very confident in analytically creating the gradient function. So here's objective function gradient. So we did this. As an aside, now admittedly I'm recording this after I did this experiment, so I'm recording this in July of 2025. I think I prepared this presentation in like March, April of 2025. Oh, that's Excel telling us that he's done. Let's see if he still is. Yep, all right, he's finished. So we'll come back to him in a moment. So anyway, in May or April of 2025, when I was creating this presentation, I thought, let's see what AI can do. So I gave both Grok and Perplexity AI the objective functions that you'll see throughout here. And it said, please compute the gradient. And it got some of them right and some of them not so right. So if you're worried about AI taking over, just know that it still hasn't passed sophomore level calculus. Or at least it hadn't back then. Maybe it's a genius now. Who knows? All right, but anyway, we create our objective function gradient. But wait a minute, you say, look, hey man, I was 19 when I took Calc 3. I don't feel confident enough in my skills today to just write down a gradient function. Okay, fine. Well, do your best. But then here's the thing is that you don't have to trust your skills, you can just check them. And so that's the point of this right here is what's going on here is this is a numeric differentiation in R. That's what's going on right here. And you just say, hey man, I want you to compute a gradient. And it says, of what? You say, well, this objective function. It says, where? Right here. That's what I want. So we right here, we generated a random number, a random vector. And now we're going to look at what R says is the numeric derivative there versus what our formula says. And they go, okay, well, we're good at the fourth decimal place. Well, I feel pretty good about that. So my skills must not be that terrible from being an undergrad. And moreover, we recognize that the Jacobian is precisely just the matrix. The Jacobian is a constant. It's just a constant matrix. Again, that's not always the case, but it is in this case because all of our uh, inequalities are linear. So we go, that's easy enough. We already created the matrix, so we're in good shape there. But again, if you're not feeling confident, if you're like, man, Calc 3 was a real long time ago, that's fine. You can use numeric differentiation in R to calculate Jacobians or estimate Jacobians. So you say, hey, give me this Jacobian of what? Of this. Where? Right here. Okay. And then you compare that with the result. We're good at the 9th or 10th decimal place. Yay us. We're feeling pretty good about that now because now what we've done analytically coheres with what comes back numerically. And so now what we're going to do is we're going to run the exact same constrained optimization, but now we have provided the function performing the constrained optimization with formulaic derivatives, gradients, and Jacobians. So now let's let this guy run and see what comes out of it. So there it goes. And bam, look at that. We got a near tenfold difference in runtime. So previously, each of these runs of the auglag function took 1.8 seconds. By providing it with formulae for the gradient and for the Jacobian, we got that down to 0.18 seconds per run. So we've just improved the efficiency of this by 90%. So yay us. Okay, so now let's go back to Excel and see what we're talking about with respect to the precision and what it means for things to be the same, right? Okay, so back in Excel land, what do we see? Well, in these group targets here, this is what we were saying. Let's look at it in the PowerPoint. That's what we were saying. Let's go back to here. Is at the 8th decimal point, records 5 and 6, things change, right? They're no longer, quote, the same. And so then that's highlighted in the PowerPoint, but you see it here directly in the Excel when you look at records 5 and 6, is that things are different there. at the 8th decimal place. So what do you do? Well, for one thing is, first of all, you don't panic. But the other thing is you say, look, I'm just simply going to select a tolerance, and so that's another piece of this. Is you have to select a tolerance of what you're going to mean by the same, because at machine precision, things can get really crazy out of the 15th decimal place. You're going to create a tolerance and say up to this decimal point, that's what I'm considering things the same. You say, okay, great. Well, what happens when you do that? And the answer is you get something that looks like this. So on this tab here, what did we get out of that? Well, when we ran the constrained optimization and we look at the group, so if you look at the formula for the grouping here, what I've selected here is I've selected things being the same at the up to the 8th decimal place. You can see that in the rounding function here. It's at the 8th decimal place. And it said, okay, well, if 8 decimal places is what you mean by the same, then what comes out of this is you get 70 groups from the original 101. Have a nice day, sir. Okay, well and good. What happens when we group those things together and we see, well, dude, it's still not increasing. What's going on here? What's going on? It's still not increasing. It's increasing more than it used to be, so we've made some progress, but it's not totally increasing. And the answer is, remember that what we were doing by doing the constrained optimization problem was a necessary condition, right? Which is that the definition of a grouping is a vector of increasing components where the same components imply that we've grouped together those two records. But we've gone about it the opposite way. We said, okay, well, we'll just solve for a vector of increasing components and hope that the same components give rise to a grouping, which gives rise to increasing target weights. And indeed, has for the most part, not totally. Okay, kind of a bummer. Oh well. But there's a key thing to observe here, which is that, look, we've reduced the problem. That's the key. We've reduced the problem. We used to have 101 things we were trying to group together. Now we have 70 things we are trying to group together. And so now what we do is we simply iterate this process. We say, okay, we got these 70 guys. We want to group them together somehow. All right, fine. We've got our constraint column. We want all these guys greater than or equal to 0. We've got our Jacobian matrix that goes along with it, except now it has 70 columns and 69 rows. And so now we just do the same thing. We say, okay, solve this constrained optimization problem. So we put solver to go about his merry way. So again, minimizing the sum of squared errors, changing these variables here in column F. Subject to the constraints, please make everything greater than 0. And away it goes. So it's going about doing its thing. Okay, so with that in mind, let's go back to the PowerPoint now. Okay, so everything I just said, what that means is that we need to update our strategy. So the strategy used to be solve the constrained optimization problem. How do you do it? Well, you recall that hey, if we have a vector of increasing components where the components are the same is the mean of the things that we group together, then we recall that the mean minimizes the sum of squared errors. That gives rise to this. And we're going to posit the grouping from the solution vector. We just found out, well, it's great in theory, but it doesn't always work. Nonetheless, that's fine. We'll just test the grouping, and then we will reduce to the level of the current implied grouping, and then we'll just keep doing that until we get a set of things that actually have increasing target. Okay, so now that Excel's off doing its thing, let's talk about constraint mapping. So here's the way to think about this, which is that when you are using constraints, when you're doing constraint optimization, each one of your constraints adds to the complexity of the constraint optimization problem. Should be no surprise. So if you are grouping n values, that requires n minus 1 constraints. Well, why? Well, because 2's got to be bigger than 1, 3's got to be bigger than 2, 4's got to be bigger than 3, and so on. And so what that does is it gives rise to n minus 1 constraints. Why do we care? And the answer is, well, because each constraint introduces at least one additional parameter to the Lagrangian. And so when you're using the multiplier technique here, when you're using a Lagrangian, that's in the case where all of your constraints are equal, you get an additional parameter in your Lagrangian. The method of Lagrange multipliers, again, known in the 1800s. It's just that only now we have the computational capacity that we can actually implement it at scale. In the case when you are doing inequalities, then what you have is what's known as an augmented Lagrangian, and that is why the function is called the auglag function in the Alabama package. So what you have then is in your augmented Lagrangian, you have 2n minus 1 parameters. So you've essentially doubled the computational complexity. But sometimes it is possible to map Rn into the feasible region. I'm guessing not always, but sometimes you can. And so the way constraint optimization problems work is, ideally, right, wherever you land for your answer, you want it to be in what's known as the feasible region. The feasible region is where all of your constraints are satisfied. You can't just go wandering anywhere looking for a solution throughout all of Rn, although that's what you do in an unconstrained optimization problem. But sometimes you can map all of Rn into the feasible region. How do you do that? Well, you go back to thinking about the problem as we started talking about it when we were talking about the Jacobian, which is we say, well, look, instead of thinking in terms of I want things to be increasing, a vector of increasing components, one way you can conceive of this and think about it is that no. What I really want is I want the differences between my components to all be non-negative. And so when stuff is increasing, that means that y2 minus y1 is positive, y3 minus y2 is positive, y4 minus y3 is positive, yn minus 1 is positive. Or non-negative. And so you say to yourself, well, what functions do I know that make things positive? And if you do a lot of modeling using GLMs, you go, I know a function, the exponential function. The exponential function always makes things positive. And so I'm going to reformulate my problem in the following way, is that you can hand me any vector you want from Rn, and I'm going to say, okay, cool, here's what I'm going to do with it. I'm going to just take the first component as whatever it is. But then the second component is going to be the first component, x1, plus the exponentiation of x2, like this. And then once I've done that, I know that y2 minus y1 is just going to be e to the x2. It's going to be positive. So yes, we find ourselves in the feasible region. y3, I'm going to take to be x1 plus e to the x2 plus e to the x3. And now when I take the difference between y3 and y2, what do I get? Well, I get e to the x3. It's exponentiated. It's positive. We're in good shape. So this transformation here, you hand me any vector from Rn, and I hand you back this transformation implied here. It's this guy right here. I know that the output of this is in the feasible region, and then I'm simply going to take this and put that in my objective function and say, please maximize this thing. And so by composing this function which maps all of Rn into the feasible region with my objective function, I'm going to transform this constrained optimization problem into an unconstrained optimization problem. Now, you might argue with me and say, well, hey, pal, look, exponentiation makes things strictly positive. So, you're sort of leaving off the table, or leaving on the table, depending on how you're looking at it, the case where these two guys are equal to each other, the y4 equals y3. How about that, pal? And the answer is, who cares? And the reason why I say that is because at machine precision, you can't tell the difference between, 10 to the negative 32nd power and 0 anyway. And so it's perfectly fine for things to be have a very small positive difference, because again, you have already declared ahead of time what tolerance you're using to declare things to be equal anyway. So it's not really a problem when you move from the mathematical realm into the numeric realm. There is a difference between computation and mathematics. Okay. And so now we're in good shape because we got this function g and it maps Rn into the feasible region. So we are going to go take a look at how that looks here in R. So let's go to our good friend R. Okay, so now that we're looking in R, what we're going to do, how are we going to represent, how are we going to represent the function that we just created in R? Let's go back to that. So that is to say, we've got this function right here. How are we going to represent this function in R? Well, let's first again think about how this would look in Excel. So we go to Excel. And we say, oh, okay, cool. Look, he's done working. Mr. Solver's done working on the 70 group problem. Sure, it's taken him long enough, isn't it? Anyway, we'll let him work some more in a moment. But first, we want to talk about how to create that function here. So what we're going to do is, like I said, we have to somehow map any vector in R into the feasible region. How does this look in here? And the answer is, well, here's our group target. And how is this defined? Well, look here, we've got what's going on in here. Well, again, we've got our good friend matrix multiplication. What's being multiplied? Well, clearly column H here is being multiplied by some matrix. What is that? And the answer is right here. So going back to the function here, so going back to our good friend Mr. PowerPoint, over here, what do we have here? What we have is we are looking at sums of exponentials. We're exponentiating stuff and then we're adding it up. So you can see that right here in the summation notation here. We're exponentiating stuff, we're adding it up. That's what's going on. So somehow we need to represent that first in Excel. So let's go back there and take a look. All right, so how do you represent adding up a bunch of stuff? Well, the way you do that is you exponentiate. So you can see we got the exp function here in Excel. That's exponentiating stuff. What are we exponentiating? Well, we're exponentiating all the stuff here in column H. That's what we're doing. Oops. That's what we're doing there. And then what are we doing? Well, we're multiplying it by a matrix. What matrix? This matrix. What is this? This is a lower triangular matrix. Why are we doing that? Because when you multiply by a lower triangular matrix, you are adding up the components of the vector that you are multiplying by it. So what comes out of the first row is just the first component. What comes out of the second row is some of the first two components. What comes out of the third row is the sum of the first three components, and so on. And so again, you've got 100 different pieces to this matrix here. And that is that. And so that's how we are representing now the parameter. We're taking column H here is what is varying, but then we are transforming that in column I to give rise to the grouped target. That's what's going on. Then we compute the weighted error, and here's the total error there. So you can run this if you like in Excel. We will not be running it here. Just for the sake of illustration, though, we will let this guy finish out. So we'll encourage Solver to try just a little bit harder. Let's see if we can't get that total error down a little bit. So we're going to let him go about his business, and we will go back now to R now that we know how we want to represent things. Okay, so in R, now that we know that we want to have a lower triangular matrix, create one of those things. So that's what we have right here. It says create auxiliary matrix. There's our lower triangular matrix. How does this look? Looks just like this. Oh, looks like Looks like Mr. Solver's done. Let's see if we can do anything more. Nope, he's done. He's done. All right. So anyway, back here in R, we got this lower triangular matrix. How does it look? Well, because it's just ones and zeros, R is not trying to waste any space. It simply represents them as logicals. So you got true, bunch of falses, true, true, bunch of falses, true, 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 bunch of falses, and so on. All right, so that's that. And so now we define our new objective function. So as we said previously, what are we doing? We're exponentiating our components, right? And then we are multiplying that by the lower triangular matrix so that we get the sum of our exponentials. And then we are looking at the weighted squared error between those two values. And then we're adding it up. And so that's our new objective function. Create our initial value here. And again, we're just going to run this guy, and we're not even going to worry about doing numerical or formulaic differentiation. We're just going to let it run numerically and see what comes out of this thing. So that thing is going about its business right now, and we'll see what happens there. Okay, so somewhat unimpressive, right? I just made this big speech about, hey, look, if you can map into the feasible region, it's going to save you some time. And it says, are you sure? Because look, we just did it, and although it was better than the constrained optimization we originally ran, it still took 1.18 seconds per round. So now we're using just the straight optimization routine in R, the optimum function. Better than the constrained optimization problem, but not nearly as good as the constrained optimization problem with analytic derivatives, with formulaic derivatives. Okay, fine. Well, we're going to create another auxiliary matrix, an upper triangular matrix. Why are we doing that? Well, because we're going to create the gradient of our new objective function. That's why we're doing that. And again, we're feeling kind of fragile about our differentiation skills, so we're going to compare that against numeric differentiation. Lo and behold, okay, we're good at the fourth decimal place. We're feeling good about ourselves, so now we're just going to let this guy run. And there we go. Boom. All right. So now we're already done. Look at that. That was so fast. So fast. So when we have transformed, so when we've done two things, right? We've transformed our constrained optimization problem to an unconstrained optimization problem. And we have also provided it with a formulaic derivative instead of relying on numeric differentiation. Now look at the benefit here, is that the original problem, no formulaic derivatives, numeric differentiation, constrained setup, that took 1.8 seconds to solve. By providing it derivatives, we were able to decrease that by 90% down to 0.18 seconds. And by reformulating that as an unconstrained optimization problem through this mapping, we were able to get that down to 0.02 seconds. And that's another 90% decrease in runtime. Now, I know you might be saying to yourself, well, hey, look, Ian, is 1.8 seconds too long? But we'll come to why you care momentarily. But just notice that by doing a little bit of work up front, by thinking about constraint mappings and by provision of formulaic derivatives, we've been able to get this down to 0.02 and 0.03 seconds per run. Okay, well, I want to make a point about exponentiation, though. So check this out. So we're just going to create a large vector of random numbers here, like that, and now we're going to exponentiate all of them, and we're going to do that 10 times in a row. Just take a look at the average time that takes. Okay, and so why am I taking you through this? Okay, so that took about, exponentiating all those numbers took about 0.72 seconds. Now we're going to do the same thing, except we're going to square the numbers and see what happens. And bam. Okay, so look, that took 0.03 seconds per time. Obviously, there is a very large difference between these two values here. And so that would suggest that indeed, squaring is computationally less expensive than exponentiation. Okay, so returning then to the PowerPoint, yeah, returning then to the PowerPoint, let me pass this slide here. Uh, there's something else to consider, which is that sometimes exponentiation, it creates large values, right? Like there's a reason we talk about exponential growth and we talk about it in hushed tones, right? Because stuff's growing real fast. And so although thus far we've been working on toy problems, exponentiation can yield some really large values. And so when I was using this in practice, what I had noticed was I was sometimes getting errors thrown. I was getting warnings because of things overflowing and whatnot. And I think that was some of that was because exponentiation yields large values. The other thing is that the computation itself, of course, because exponentiation, when you write it as an infinite sum, contains a squaring term. Mathematically, we know it's more complex computationally, right? Because squaring is simply one piece of this expansion here, and that we just confirmed that when we were looking at the R code. And so what we're going to do is we're going to reformulate this problem one more time. But this time what we're going to do is it's instead of saying, all right, I'm going to let my differences be squares, we're going to say, or exponentiation, we're going to say, I'm going to let my differences be squares. And so this right here is still a mapping into the feasible region, except now instead of summing up exponentials, we're summing up squares. So it's computationally less expensive, and you're gonna avoid those large values. It maps into the feasible region. So let's go back now to our good friend Mr. R and see how this works in practice. Okay, so clear that out. Create our new objective function here. So instead of exponentiating stuff, we are going to square it. Then we're going to add up the sum of those squares. So there's our new function. Create our new initial value. We're not going to bother checking our arithmetic now. We're feeling pretty good about ourselves. So now we're going to let this guy run. So we're going to let this guy run again, just for the sake of, what would you say? For the sake of comparison, we're going to run it with and without formulaic derivatives. Okay, so there it is. So let's see here. Without formulaic derivatives, slightly beat the exponentiation constraint mapping, 1.08 versus 1.18. Now we'll do our gradient. Check that. All right, things look good. All right, so now we're going to use the squaring constraint mapping. Let that guy run. Okay, so there you go. And we got a slight improvement there, 0.023 versus 0.027. And so now we can do, and what did we just do? We just did a constraint optimization problem in 0.023 seconds. So why is speed so important? And the answer is, well, look, sometimes it's better to discretize your ordering variable than use the raw values. So what do I mean by that? Well, what I mean is that sometimes your target variable is very volatile. So in the insurance industry, loss is it's a very volatile, we call it pure premium. That was, of course, earlier in the presentation. It's a very volatile variable. And the reason why is, you know this from experience, most people aren't getting into car accidents on a daily basis, right? So the loss associated to most people is zero. So it's 0, 0, 0, 0, 0, 0, 0, 0, 0. And then every now and then, bam, $50,000, 0, 0, 0, 0, 0. And it's even worse with home insurance, and it's even worse when you're doing with things like medical liability, because then it's like 0, 0, 0, 0, 0, 0, 0, 300,000, 0, 0, 0, 0, 0. So sometimes you have a very volatile target variable. And although you might have an ordering variable which is very precise, uh, uh, it takes a lot of different values, your target phenomena might be so volatile that it's even this grouping algorithm it just won't pick up a lot of the signal. And so then sometimes it's useful to group the values of your ordering variable together. You discretize them, you chop them up, start grouping those guys together. And then on that reduced data set, try to perform the grouping exercise. Okay, so with that in mind, we go now back to RStudio. So coming back to RStudio, we introduce the increasing groups function here. So here we go. And so what is this doing? Well, look, it's it's performing the constraint optimization problem. It's doing everything we talked about. So it's using the constraint mapping. It's setting up the problem appropriately. It's iterating through. If the first time we do it, it doesn't give us stuff that's perfectly increasing. And then you can check to make sure that yes, indeed, things are the way they should be. So bam, look, okay. We looked at the minimum difference. It's 0. Okay, so that's good. And then you can actually just see the output of this. So it's like, all right, here's the original data set, variable weight target, ordering variable weight target, and now you can see the grouped version of it. So these guys got grouped together, these guys got grouped together, these guys got grouped together, and so on. And so yeah, we're in good shape here. It worked. Things are grouped together such that they are increasing. And of course, it did it quite quickly. All right, so the speed matters now when we're going to do 2,000 observations instead of 100. See how long that takes to go. So I mean, 100 observations versus 2,000 observations. That's obviously going to take a minute. So that, of course, is the point of all of this talk about speed, is that even 2,000 observations, we are able to group those together in 17 seconds. And you can go through the same process, right? You can look at the minimum difference among the values. It's 0, so that's good. And then we look at can't look at all 2,000 records, so we'll look at the first 250. But again, ordering variable, weight, target, and there you go. So it's just all increasing. These guys right here all got grouped together. These guys here got grouped together. Those guys are different. Boom, boom, boom. These guys got grouped together there. These guys got grouped together there. These guys got grouped together there. So we were able to do 2,000 observations in 17 seconds. Now, so all well and good. The purpose then of checking out different discretizations is as follows. That is the point of the increasing group search function. So what's going on here? Well, the increasing group search function does the exact same thing as the increasing groups function. It just does it a bunch of times over. And here's how this works. So a lot of the inputs are the same. But you have this additional input, 2 additional inputs. One is the discretization vector here. And so basically what you can do is you can tell the increasing group search function, hey, look, what I want you to do is I want you to try discretizing my ordering variable in this way, that way, this way, that way, this way, that way. First, discretize the ordering variable, then try to create increasing groups. And then try to discretize it this different way, and then try to create increasing groups. And then the raw discretize input here says, and also try to do it just on the raw data itself and see what goes on. Now, because these runs here, when you're doing all these different discretizations, don't rely on each other, that means it can be parallelized, and that is the point of the cluster parameter here, is that you can parallelize this. It will go faster when you do that. And so what we've told this thing to do is we are actually taking a look at, I guess that'd be 102 different possibilities here, because we're saying this sequence function here in R, what's this saying? It's saying, look, consider the sequence 10, 20, 30, 40, 50, and so on, up to 1,000. Okay, so that's 101 different possibilities. And it's saying, I want you to chop my data into 10 segments of roughly equal weight according to the ordering variable, then try to create increasing groups. Then look at the error associated with that and write it down. Okay, now at 20, chop my data according to the ordering variable into 20 groups. Try to create increasing groups, take a look at the error, write it down. Then I want you to chop my data into 30 groups of roughly equal weight on the basis of the ordering variable. Then create increasing groups, write down the error, and continue to do this. And again, the raw discretizes, also do it on the raw data. And then let's just see what happens. And let's see which one of those things actually gives rise to the best error, which of course is the smallest error. And so what it's doing is it's actually performing the increasing groups function in there 102 times. And so that's the reason speed matters, is because it allows you to explore all sorts of ways that you might try to wrestle these functions to get increasing groups from them. And because we were able to do it so quickly, we were able to take we were able to group 2,000 observations 102 times in only 2.5 minutes. It's very, very quickly, very fast. And so that allows us to sort of look for, if you will, the best grouping of things in a reasonable amount of time. All right, so we'll just check to make sure everything's kosher there. So this checks to make sure that our group is proper. Here we'll check to make sure that things look good, and lo and behold, again, they do. Scrolling up, we'll look at the first 250 records. And so again, these guys have been grouped. These guys have been grouped. These guys have been grouped, and so on. So now we will return to our PowerPoint presentation and finish out the presentation here. Okay, so because you might have a target variable that has high volatility, like auto insurance loss or just insurance loss in general, sometimes it's better to discretize your ordering variable than to use the raw values. And the speed of the algorithm helps us to do that in a reasonable amount of time. Here is how we're going to use this, however, in this particular project. We now have an answer to how you group a categorical variable that has a large number of values. And so you just have a few values in your categorical variable, red, blue, and green. It's not so terrible. But when you have a bunch of them, right? So like, I believe there's about 40,000, 45,000 zip codes in the United States, although of those, only about 30,000 are, like, if you will, real zip codes. Like they're not army bases, they're not PO boxes, that kind of thing. Nonetheless, 30,000 is like a lot, right? There's about 4,000, 3,000 counties, if you want to do things at the county level in the United States. So again, like that's a lot. How do you group these things together in some reasonable fashion? And the answer is, well, your data might look something like this. So it's like, here's my zip code, got a bunch of exposure there. So we've insured a bunch of people there. Average loss is about $100. Zip code 2, we insured one guy there. He had no loss. So what does that mean? Does that mean that we should, everyone in zip code 2 gets free insurance? Is that what we're going to do? Then in zip code 3, here we got one guy, we insured him, and he had $1 million loss. So now everybody in zip code 3, they have to pay $1 million. And then zip code 4, again, a lot of exposure there. Average loss about $200. Okay, so well, the way that you handle this is you build a predictive model by any means necessary. And so what I mean by that is, I know the point of this is to produce models which are simultaneously explicable and precise. Well, that's two conditions. So before doing that, you first create a model that's just precise. You create a model using a neural network. You create a model using XGBoost. You create a model using random forest, something like that. And what that will allow you to do is it will allow you to order the values of your categorical variable. So what you can do is you can summarize to the level of your categorical variable, whatever it is, zip code, county, VIN, right? Or, what make, model, something like that. And your model is going to tell you how to order all of those things. And then what you can do is then you can just march down and say, okay, well, on the basis of that, looks like, yeah, okay, $0 and $100. Yeah, but, according to the model, these guys should probably be grouped together. So we're going to group these two guys together, probably charge them, slightly less than $100, maybe, I don't know, $99.90, something like that. And here, we're going to group these guys together as well, because the model says, yeah, they should probably be really close to one another. How would you do this in this particular case of zip codes? And the answer is, well, what you could do is you could build a model using geodemographic variables, right? There's all sorts of data sets that have geodemographic variables in them. You use those variables to model your phenomena of interest, and then that gives rise to a model, which then gives rise to an ordering of the values of the zip code, which then allows you to group the zip codes in terms of increasing pure premium. Same thing at the county level. You could do it there. Same thing at the make model level if you're dealing with cars, is that you take information known about the vehicle from the VIN, you build a model by hook or by crook using that data. That gives rise to an ordering variable, that's the model. And then you say, okay, sort my data by the model, and then create groups of increasing pure premium. And that's how you can get a reasonable grouping of makes and models. Okay, so in summary, what did we learn? Well, we learned that a necessary, although not sufficient, because that's why we have to iterate, a necessary condition for grouping is a solution to a constrained optimization problem. We learned that, in particular, it's fine if you only do something once to not bother with numerical or analytic or formulaic differentiation. But if you're going to be doing something over and over again, it's absolutely worthwhile to provide formulae, to provide actual functions for your derivatives, for your gradients, for your Jacobians. They materially improve performance. This has always been the case for me whenever I've done this work. Moreover, sometimes, if you're lucky, you can find a mapping of all of Rn into the feasible region, and that allows you to trade your constrained optimization problem for an unconstrained optimization problem. Moreover, if you're willing to consider different ways to accomplish the same thing, there is value in selecting the least computationally complex function that, in fact, does that. Moreover, if your target variable has a high variance empirically, that is to say, it's been my experience, it is worth considering grouping different discretizations of your ordering variable. And finally, and this is of course the overarching theme of this, is that I hope it's clear that both mathematical and computational reasoning both have their place. I hope you found this presentation to be useful. If you have any questions, please leave them in the comments.